Yesterday I said we are going to be looking at the concept of flip-flop. Am I correct?
Yes, sir.
But before we go into the details of flip-flop, I want to explain this first. Memory, the PLC memory bits. Okay, so um, since last week in our programming, we have been using addresses such as I0.0, Q2.0. Basically, we have been using the process image input and the process image output. We have been using the input addresses and the output addresses for programming. Okay, but you might be in a situation where you want to have a kind of placeholder memory. Say you are writing a, maybe let me just use the word complex program, where you want to have a placeholder for your signal or your variable. You need, there are, in Siemens there are two category of memory you can use for that. You can use the memory addresses, the memory addresses, and you can also use the data block. Okay, but for the purpose of this class, we are only going to be looking at the memory address. So just like I was saying about I0.0, or let me say, just as I was talking about the input addresses and the output addresses, we also have the memory addresses. So you have the bit memories, okay, which you'll be seeing something like M0.0, M0.1, which are for the bits or Boolean signals. Okay, and then you have the MB, which is the memory byte, and you have the MW, which is the memory word, and you have the MD, the memory double word. So if you have a Boolean signal that you want to probably temporarily store somewhere for later use, you can use the memory bit M0.0. Also, if you have your values, your variables that you want to store temporarily in a memory space so that you can use later on in the program or for some comparison or any other instruction that you might be thinking of using later, you can store the value in the likes of the MW and the MD. Okay, so I just say I should go through this because we are going to be using it going forward. Okay, so what am I saying in essence? Let's say you have a particular pump, okay, that needs to come on, but under certain conditions. Okay, so and then let's say you have a situation where when you press a button, okay, and then when which approach first? Let's say when you have your start and you have your stop condition, okay, to indicate, let's say, in operation. And you have a sensor in which you want it to sense, you want it to activate the pump when there is nothing in the tank, for example. Okay, so but you need the system to be in operation. Okay, so you can then use, if this is a normal address I0.0 and I0.1, for example, your in operation can take an address of, let's say, M0.0. Thank you. Okay, your in operation can take the address of M0.0. This particular address is in the memory, is part of the memory address of the PLC. So it gets stored in the PLC. Okay, so that okay, start, stop, and then this it serves as a placeholder for your signal. Then whenever your sensor now senses that okay, there is nothing in the tank, the pump can start. Okay, so you will be using more of these memory bits as we proceed in the program. Okay, so now back to the concept of flip-flop. A flip-flop is a digital electronic circuit that switches between two states, 0 and what, and 1. And it is such that it only needs let's say you have a lamp now, okay, that you want to put on, and you are going to be putting it you are going to be using two different push buttons, your start and your stop. So your start can serve as a set for that flip flop, and your stop can serve as a reset for the flip flop. And it is such that when you press the button, the signal of this the signal is retentive. So you don't need to hold on to the button. Once you press the button once, the signal sent to that flip flop is retentive, and that particular lamp will be on until there is a signal on the to reset it. So it will remain on the signal state. It will be at it will remain at 1 until it is reset to 0. And if it is reset to 0, it will remain at 0 until you set to 1 again. So in theory, so let's now say you have two push buttons. Okay. Okay. Two push buttons. One is serving as set, one is serving as what? As reset. And you have a lamp that they are trying to turn on. So if you press this button, the lamp become what? The lamp turns on. Okay. Even when you must have released the button. Are you with me? But by the time you press this other button, which is serving as reset, the lamp turns what? Turns off. Okay. The lamp turns off. When none of them is pressed, it's going to take the state, the last state. So if it was the set state that it has, it will remain in that set position until there is a reset. If it was the reset state that is the last, it's going to take that reset position until what? Until you set again. Okay. So in theory, when you press the two at the same time, what you're supposed to have is an undefined state. It's an undefined state. So it is such that when you press the set button, the lamp should come on and remain on until you press the reset button. And if you press the reset button, the lamp should remain off until you press the set button again. So when you are not pressing any of the button, the last state is what is going to retain. And in a situation where you press the two, it is supposed to have an undefined state. You should know, you don't know whether it's going to be on or off. That is in theory. But when we now come to PLC programming, it's in TIA Portal to be precise. So we have two type of flip-flop in there. We have two type of flip-flop. We have the okay. So we have two type of flip-flop. You have the SR flip-flop and you have the RS flip-flop. Okay. So what's SR flip-flop? Set and reset. or set reset flip flop, and this one is reset set what flip flop. How does it work? So I will not, I might not get the exact diagram right now, but it is such that you have a signal state of set, and you have that of reset, and your, let's say your output, let me put en something. Okay, so this is our set reset, this is our SR flip flop. Okay, so it is such that, say you have something like I0.0 here, and then you have something like I0.1 here to reset the flip flop, and then you have your output Q, let's say 2.0 here. Okay, it is such that when you press this button, this output become this flip flop becomes set, and then okay, there will be a kind of a storage area here, an output here, M0.0 inside your program. It can also be, you can also put your output address there, but let me use M0.0 here. Okay, so it will be such that when you press this button, this particular output will become set. That is, this will be equals to what? 1. By implication, the RLO at this point too will be 1. Okay, the RLO at this point too will be what? Will be 1. So, and it will remain 1 until this is pressed. So until you press the reset button, this will remain 1. By the time you now press on the reset button, this will become 0. Are you with me? So say if I did not press, if I 0.0 and I0.1 is not pressed, I mean are not pressed, okay, the last signal state is retained, whichever one. Maybe it was the last, it was the set that I pressed last, or it is the reset that I pressed last. It will retain the signal state. Okay, so now in a situation where for this SR flip flop, if you now press only, if only I0.0 is pressed, your output is set, that is 1. Okay, and if only I0.1 is pressed, your output is reset, that is it will be 0. So what will happen if we press the 2? In theory, but in PLC programming now, in TIA Portal to be precise, one will have higher priority over the other. One will dominate the other. In the case of SR flip-flop, reset dominates set for SR flip-flop. So it means that if you press your I0.0 and I0.1 at the same time, I0.1 is more powerful for SR flip-flop, and for that reason, what you have is your flip-flop will be your circuit will be reset, and hence your output will be 0. It will not come on. Reverse is the case for for RS flip-flop. Okay, so for RS flip-flop, like I said earlier, set dominates. Okay, set dominates. So when you have your I0.1 serving as the reset, okay, and your I0.0 serving as the set, okay, say you have something like M0.1 here, EN, okay, that's your output, Q2.1 for example, okay. So when you press only I0.1, your signal state at this point will be what? 0. Your RLO at this point will be 0. Okay? Until, and it will remain that way until you press on the what? Set. So when you press on set, your RLO becomes what? 1. Okay? And then it will remain in that state until the reset is pressed again. But in a situation where there is signal at these two states, that is, you press both your I0.0 and I0.1, the set dominates, meaning your RLO will be what? Will be 1, irrespective of whatsoever is going on with the reset here. Are we together? So basically, that is how flip-flop works. So let's try that out in the software TIA Portal.